Computers feel fast or slow largely because of memory, not storage, not the CPU, system memory. More specifically, DDR memory. DDR stands for double data rate. It describes how modern RAM moves data. And over the last 2 decades, DDR memory has quietly evolved. Each generation looks similar. Each one works very differently. DDR memory arrived around the year 2000. It replaced SDRAM, which transferred data only once per cycle. Typical DDR speeds ranged from DDR200 to DDR400. That means 200 to 400 MTSIS. Bandwidth topped out at about 3.2 GB per second per channel. Voltages were high by modern standards. DDR ran at 2.5 volts. What it was is simple: an early double-pumping memory system. Why it existed is also simple. CPUs were getting faster. SDRAM could not keep up. How it worked was straightforward: 2 data transfers per clock cycle. Same basic memory architecture as SDRAM, just faster signaling. Think of it like a single-lane road that allows cars to pass on both green and yellow lights. You move more cars without rebuilding the road. In real-world impact, DDR enabled early Pentium 4 and Athlon XP systems to scale. Games loaded faster. Multitasking became viable. Strengths were clear at the time: big bandwidth jump, minimal complexity increase. Limitations showed quickly: high latency, high power draw, poor scalability beyond 400 MTSS. DDR was replaced because it hit a frequency wall. Signal integrity became a problem. Power efficiency was poor. DDR2 arrived around 2003 to 2004. DDR2 was not just a speed bump. It changed how memory accessed data internally. Typical DDR2 speeds ranged from DDR2 400 to DDR2 800. Later models reached DDR2 1066. Bandwidth doubled again, up to around 8.5 GB per second per channel. Voltage dropped to 1.8 volts. What DDR2 was is a higher frequency memory with deeper prefetch. Why it existed was scalability. DDR could not reliably go faster. How it worked changed internally. DDR used a 2-bit prefetch. DDR2 doubled that to 4-bit. That means the memory grabs more data internally at once, then sends it out faster externally. Think of it like a warehouse. Instead of picking 1 box at a time, you load 4 boxes onto a cart, then roll the cart faster to the door. Real-world impact was mixed early on. Early DDR2 had higher latency. Some DDR systems felt faster at the same clock, but as speeds increased, DDR2 pulled ahead. Intel Core 2 systems benefited greatly. Strengths included higher frequencies and lower power. Limitations included latency penalties. Early DDR2 modules were expensive. DDR2 was replaced because CPUs demanded more bandwidth. Multi-core processors were arriving. DDR3 launched around 2007. This is where modern memory behavior starts to look familiar. DDR3 speeds began at DDR3 800. They scaled up to DDR3 2133 and beyond. Bandwidth reached about 17 GB per second per channel. Voltage dropped again. Standard DDR3 ran at 1.5 volts. Low voltage DDR3L ran at 1.35 volts. What DDR3 was is an efficiency-focused redesign. Why it existed was power and bandwidth. Laptops were growing rapidly. Servers needed efficiency. How it worked built on DDR2 ideas. Prefetch increased to 8-bit. Internal clocks slowed. External transfer rates increased. Think of it like adding more lanes to a highway while lowering the speed limit inside the city. Traffic flows better overall. Real-world impact was huge. DDR3 became the longest-lasting DDR generation. From early Core i7 to late FX CPUs. Strengths included high capacity support, lower power usage. Stable performance, limitations showed later. Bandwidth per core became insufficient. Modern GPUs and CPUs were starved. DDR3 was replaced because platforms needed more parallelism and lower voltages. DDR4 arrived around 2014. DDR4 looks similar to DDR3, but it is not compatible. Speeds started at DDR4 2133. They scaled to DDR4 3200 officially. Higher speeds exist via overclocking. Bandwidth reached about 25.6 GB per second per channel. Voltage dropped to 1.2 volts. What DDR4 is a density-optimized memory system. Why it existed was capacity and efficiency. More cores, more threads, more memory demands. How it worked added bank groups. This allows more simultaneous operations. Less waiting between accesses. Think of it like multiple checkout counters instead of one long line. Even if each cashier is not faster, overall flow improves. Real-world impact was smoother multitasking, better performance in memory-heavy workloads. Servers gained massively. Strengths included high density, better parallelism, lower power. Limitations became clear over time. Latency improvements slowed. Clock scaling became harder. DDR4 was replaced because frequency scaling stalled. Power efficiency needed another jump. DDR5 arrived around 2021. This is the biggest change since DDR2. DDR5 starts at DDR5 4800. Mainstream kits now run at 5600 to 6400 MTSOP. Bandwidth doubles again. DDR5 6400 delivers over 50 GB per second per channel. Voltage drops further. 1.1 volt standard. What DDR5 is a split-channel memory design. Why it existed was bandwidth pressure. Modern CPUs have many cores. Integrated GPUs rely heavily on RAM. How it works is different. Each DIMM has two 32-bit subchannels instead of one 64-bit channel. This reduces idle time. DDR5 exists because future CPUs demand it, not because current ones always need it.